equals W?
Yeah, I'm gonna go ahead and minus W equals 0 just for the process, but yes.
Okay.
All right. So from that, we get A plus B minus equals W, as Jack said. All right. What equation to unknowns? What's the other equation?
Oh, weight is equal to mass times gravity to the acceleration. No, acceleration to gravity.
All right, so going to substitution next, equals mg, all right. What equation to unknowns? All right, we did the we did the up and down equation, which I guess brainwashed is J hat, but what about the horizontal equation?
There's not one.
Okay, unless you want to write down 0 equals 0, which doesn't help us, but it is a true statement.
Is there a k-hat equation?
Yes, there is, because that will connect it to what we're talking about now. All right, if it's in static equilibrium, I think the implication is that it's just sitting right there. There's no rotation either. It is rotation in rotational equilibrium as well, which means that alpha equals 0. So just as we used F equals ma here as the template, when we're dealing with rotational, or lack of rotation in this case, tau equals I alpha is the template. This gets us our k hat equation. Now alpha is 0, because it's just sitting there. So we need to figure out the torques. But to figure out torques, we need to figure out where the axis of rotation is. But it's not rotating. So where do you put your axis of rotation for something not rotating?
Right in the middle.
Okay, anyone else?
I don't think it matters, does it?
No, it doesn't. Well, it's in the end, if you don't make mistakes, it does not matter.
But would it not just be simpler to put it in the middle? Or does that change things if you put it right in the middle?
If you got the same answers regardless of where you put it.
Okay.
So, well, without lack of any other suggestions, we'll go within the middle. So I'm gonna have my moment arm over here is a vector going this way, and we'll call that r sub a. And then I'll have a moment arm going this way, r sub b. We are fortunate in that the two ropes are perpendicular to the beam. Not stated, but hopefully implied by the drawing. There's a lab with this where I constantly emphasize make sure the beam is level, or the meter stick is level before you do your measurements, because this is where it matters. And then at one point, definitely make sure it's not level. So, A, force A. Oh, first off, if up is positive, I have it in or out positive.
Oh,
We're gonna have a k hat equation here.
it's positive.
All right. Oh, wait, no, which one? In or out?
In.
In is positive. Okay. So we have up is, I guess let's call that j hat, and then in. Okay. Or whatever letter you want to use. All right, so force A, is that positive k hat or negative k hat?
Positive.
Why?
Because if you do the thing, it's going inwards.
It would cause it to rotate like that. All right, so I have A times RA minus, well, the other one is going to try to rotate it counterclockwise, which we've declared to be negative, minus BRB equals And so now we have two equations, two unknowns, it is now solvable. So I have A plus B, let's put those on Earth 2, just cause, is equal to 60. And then I have RA is 2.5. So it's 2.5A minus 1.5B. No,
No, the one.
no, it is 1.5. Because the whole thing is 7, so this is 3.5.
Yeah.
That's 2, so that has to be 1.5. This is also 3.5 here, minus 1, so this is 2.5. Okay. Did I make a mistake?
Nope.
All right, two equations, two unknowns. How do we solve this?
You would move, let's just go with B. So it'd be 60 minus B equals A, and just plug it in.
Okay, to solve for this and plug it in here, all right? So 60 minus A, you solve for B? You said B
I
equals?
said A equals.
Okay, A equals 60 minus
B.
B. Plug that down there, so we got 2.5 times 60 minus B. Minus 1.5B equals 0. 150 minus 2.5B minus 1.5B equals 0. 150 minus 4B equals 4B. And so B is 37.5.
Is that 150?
Yes, this 2.5 times 60, I believe is
Yeah.
150. So we have 37.5 newtons up on B, and on A, would have to be 22.5. And I'm not opposed to it being some Carol's error, correct me if I did.
Okay. So you just did 37.5. A equals.
Yeah, I just did that. What about the torque from the weight? When I did my torque equation, I left that out. Why?
Is A.
Negligible.
Pardon?
It's negligible.
Why?
I want to say they're different kinds of forces, but I could be totally wrong.
It's not a matter of the type of force.
They cancel out.
Why? What cancels out?
Well, the tension from holding it is, it's counteracting the weight. So
Okay.
both of the tensions make the weight, like, make it not fall.
Okay.
So because it's not gonna move, it's not gonna fall. The tensions counteract the weight. Weight is negligible.
So here, when I wrote equal to 60, I should have written equals 0.
I see your point, never mind.
What's the formula for torque?
Which one?
For an individual torque, what's the formula? It was on the board over there.
R times.
Yeah.
R times force.
Okay. And what's R?
Radius
From what to what?
from the point of moment of force. Oh, from moment arm from force point, axis of rotation.
Other way around.
Axis of rotation, force point.
Okay. So we chose the axis of rotation to be the middle because Jack wanted it that way. What would be the moment arm?
The RA and RB.
What is the moment arm for weight?
Nothing, cause it's in the, like, cause I just said the middle, there isn't one.
Yeah. So technically, there is another term in here plus the weight times RW, but that's equal to 0. The weight is not gonna cause any rotation about the center. In that spirit, we could have also chosen, I mean, typically, you pick a point which is gonna eliminate one of the terms here. So picking the center, I would consider the second best choice. To me, the best choice would have eliminated either A or B from the equation. So if we had chosen this as our axis of rotation, then this exerts no torque, and I'll have an equation with just a B in it, and I can solve for it directly. So if I did that, so if this is the axis of rotation, then I have, let's see, the weight is trying to rotate it clockwise, which we've decided is a positive torque. So I have weight times 2.5. Let's go ahead and do 60 times 2.5 minus B times 4, because that's the distance from here to here, equals 0. So I get 150 is equal to 4B. B is 37.5. So
So if they're always in equilibrium, you recommend we would do that?
I do recommend one where you eliminate an unknown from the equation, but mathematically, as you see, it doesn't matter which one you pick.
If it's not in equilibrium, I assume it changes.
Correct. Then I need to specify that it could be in rotational equilibrium, which means there's no angular acceleration, but not linear equilibrium, which is what we've dealt with so far. Or it could be in
So what's,
linear equilibrium, but not rotational equilibrium, which means I've got a force up, force down, and they're basically spinning it like a propeller.
so the difference between linear equilibrium and static and rotational equilibrium is what exactly?
Linear equilibrium, acceleration equals 0, total force equals 0, velocity of the center of mass does not change.
Okay.
Rotational equilibrium, angular acceleration is 0, total torque is 0, and the angular velocity does not change.
Yeah.
Is that, it's basically the angular analog.
Yeah.
Are there any questions before I make it look more difficult? Before we eliminate one of the ideals of an ideal rope? All right, let's do it. I have a pulley, which I'll represent as a disc. I have a pulley. Radius of the pulley, we'll make it huge, 2 meters, about my height, a little bit more. I have a rope. We'll call this A and B. Mass A will make 4 kilograms and mass B will make 3 kilograms. No, let's pulley in linear equilibrium. There is friction between rope and pulley. We need a mass of the pulley. The mass of the pulley is 2 kilograms. Oh, I'm using 2 already. Let's see, I'm not using 3. 3. What is the acceleration?
0.
No. There's still, the pulley is still ideal enough, there's no friction here. We're also putting in the conceit that the rope does not slip. That the friction is enough to keep there's no sliding between the rope and the pulley, so when the rope turns a certain amount, moves a certain amount, the pulley turns with it.
Question. If it's in linear equilibrium, you just said the acceleration to change?
The acceleration of the center of mass is 0.
Okay.
All right, so we set up our equations. Now, because we go through the process, because there's now friction, we have a force in the middle of the rope. It'd be like if there's a tug of war between 2 people and then someone comes up the middle and starts pulling one direction, the tension throughout the entire rope changes. Or, yeah, tension changes. So, force diagram, A, B, pulley, rope. We treat this as 2 ropes now. All right, we're going through the facades method. F for force diagram.
There's gonna be weight on the boxes pulling down. There's gonna be weight on the pulley pulling down. There's gonna be tension on the ropes pulling up. Well, tension on the boxes pulling up.
Okay. FTA, FTV.
Tensions on the ropes pulling down.
FTA, FTV.
Now, quick question. Will the tension pulling up on box B and box A be the same even though they're different weights?
Will these be the same? Or will those be the same?
Will like FTA and then FTB are gonna be different numbers?
Yes.
Okay.
The computer has a problem with your question.
Is there,
It's wrong.
is there gonna be, okay, so we said there's gonna be friction on the pulley.
All right, so well, first off, pulling the rope is still massless. We haven't gotten into that conceit yet. And FTV. Where is they come in pairs. Where's the other part of this pair? Joey?
On the pulley?
Yes. And there's gonna be some force holding up the pulley. I don't know what it is. It's happening at the center, so we'll just call that Y. It's gonna be equal to the sum of those 3 forces acting down, but we don't care about that one. Coordinates, axes, which way is B gonna go? Up or down?
Down.
All right, so let's just go ahead and, I know it's gonna accelerate downwards, we're gonna make that positive. A is gonna accelerate upwards, make that positive. And which way will the pulley accelerate?
Outwards.
So the masses are doing this,
Mm-hmm.
so the pulley is doing,
So,
my guess is that, like, I'm just thinking the center of the pulley, and because we're going this way with the acceleration, I'm putting my hand like this, like, I guess straight forward and going downwards towards the angle of acceleration.
The back
Towards
wheel.
acceleration.
I didn't quite follow everything that you did right there. The pulley, I mean, yep, it is indeed going in. The pulley is gonna rotate this way.
Okay.
Yeah.
What position do you start at with the pulley? Just the middle?
When you say start at, I mean in terms of the hand?
Yeah, the hand
Yeah,
thing.
the thumb is the axle, so that or axis of rotation, since the axis of rotation is in the middle of the pulley, it's either gonna point like that or like that.
And because the acceleration is going that way, we're going, like, because it's rotating this way.
Yeah, that would be
Yeah.
inward. All right, so we'll make that positive. Slap on I, J, and K if you want. So our equation, jump to equations of motion. I've got FTA minus WA is equal to m sub A times little a. And I've got WB minus FTB equals m sub B little a. All right, so those are the two equations we would have gotten from chapter 4, but we are more sophisticated now. We've got the pulley. The moment arms are from the axis of rotation to where the force is applied. There's RB and RA. It is circular. So we're dealing with a force that is perpendicular to the moment arm, so that makes life simpler. FTB is the positive torque because it's trying to rotate the pulley into the board, and FTA is trying to rotate it out of the board. So I have RB, FTB. Well, actually, it's just R. RB and RA have the same magnitude. Minus